Welcome back to the deep dive. Today we're on a mission to really unpack chapter 25 from our source material, and we're diving into the subtle but incredibly important world of molecular solids.
It's a real change of perspective, this chapter. I mean, if you're used to thinking about materials like metals or, say, ceramics, you're always thinking about these strong, very directional atomic bonds holding everything together.
Right, a continuous lattice of atoms.
Exactly. But here the building blocks are already, well, complete. They're neutral molecules, things like water or sugar or carbon dioxide.
So the central question for us becomes, how do these discrete, perfectly happy little molecular units decide to stick together and form a stable solid?
That's it. And our mission today is to explain every major idea, every definition, every structure, and all the consequences of the, well, often very weak forces that govern this huge class of materials.
Okay, so let's start right at the beginning with the core definition. What is a molecular solid?
Well, structurally, it's defined pretty loosely as a solid where the primary building blocks are conveniently described as distinct molecular units.
So not individual atoms.
It's not individual atoms, it's a collection of molecules.
Yeah.
This immediately sets them apart from things like silicates or many ceramics, which you really have to think of as a continuous network of repeating atomic units.
And these molecular solids are usually based on elements like carbon, hydrogen, oxygen, nitrogen, right, the lighter elements.
That's right, which naturally brings us into the realm of organic chemistry,
Right.
the chemistry of molecules and living systems, or derived from them.
Yeah.
But here we're broadening that to include synthetic things too, like polymers and even fullerene-based solids.
Okay, so what's the most important characteristic, the thing that really sets them apart?
It's the relationship between the internal forces and the external ones. Let's take an H2O molecule. The covalent bonds holding the oxygen and hydrogen atoms together inside that single molecule are incredibly strong.
Okay, rock solid.
But then you ask, what ties one H2O molecule to its neighbor in an ice crystal? And the answer is much, much weaker intermolecular interactions. We call this the weak link.
And the consequence of that weak link has to be profound. I mean, if the glue holding your material together is weak, then the material itself is going to be weak.
Absolutely. Mechanically soft, it'll have a low melting point, a low boiling point. It's exactly why ice melts so easily, why dry ice sublimates right in front of you, and why you can crush sugar crystals with almost no effort.
The entire stability of the crystal lattice is it's dictated by this really weak cohesion.
Precisely. And the primary weak forces we're talking about here are the van der Waals forces, which you might also hear called London dispersion forces.
Okay, let's break down that mechanism. How do they actually work?
Well, they're purely attractive, and they come from instantaneous fleeting dipole moments. You have to remember that electrons are always moving. They're in constant
The
motion.
cloud of probability, right?
Right. So at any given nanosecond, a totally neutral atom might have a temporary, momentary imbalance in its charge distribution. One side is a little bit positive, the other a little bit negative.
So it creates a temporary little magnet, a dipole.
A temporary dipole, exactly. And that temporary dipole can then induce a corresponding dipole in a molecule right next to it. And for that fleeting moment, those two dipoles attract each other.
But it's crucial that this interaction energy falls off, what, rapidly with distance?
Incredibly rapidly. The attractive force often scales with 1 over the distance to the 6th power. So 1 over to the 6th.
Wow, okay.
That steep fall-off means the molecules have to be extremely close for these forces to matter at all, which gets us right back to why the overall cohesion is so weak.
But there's a huge exception to that weakness, isn't there? One that really defines the structure of, well, the most important molecular solid we know, the hydrogen bond.
Yes, and we need to be clear. Hydrogen bonds are still intermolecular forces. They're still much weaker than a covalent or an ionic bond.
But they're much stronger than a typical van der Waals interaction.
Significantly stronger, yes. They form between 2 or more electronegative atoms, like oxygen or nitrogen, and they're mediated by an electropositive hydrogen atom. You'll often see it described as an AHB dipole interaction.
So unlike the random van der Waals forces, H-bonds are specific, they're directional.
Yes, and when a structure can form a whole network of them, like water does, the cumulative effect is massive. It's enough to fundamentally change the material's properties and make it behave anomalously compared to most other molecular solids.
And this whole idea of weak but specific interactions, that leads us right into the grand theme of this chapter, doesn't it? Self-assembly.
It really does. A key attribute of all these multi-phase molecular systems is their ability to self-assemble on all sorts of different length scales. This is how you get from basic molecules to polymers to macromolecules and eventually to incredibly complex biological structures like proteins and DNA.
All right, that's a perfect place to start. Let's unpack section 1. Simple molecular crystals and self-assembled structures. And we have to begin with the most familiar and most vital molecular solid on Earth. Solid H2O, ice.
Water is just. It's exceptional. Its phase diagram is unbelievably complex. We know of at least 9 different crystalline forms, or polymorphs, depending on the temperature and pressure, and there might be more.
The form we see every day, though, is hexagonal ice. Ice, IH. That's what's stable at standard temperature and pressure.
Right. And if you look at its structure, like in figure 25.1a, it's all built from oxygen atoms that are tetrahedrally bonded. Each oxygen is covalently bonded to its 2 hydrogens.
Okay.
And then it's hydrogen bonded to 2 other hydrogens from neighboring water molecules.
So the key takeaway from that structure is that it's really open, isn't it? It's an expanded lattice.
It's a very low-density structure,
Yeah.
yes. The specific geometry of those tetrahedral bonds creates these large voids, big empty spaces, in the crystal, and that is the exact reason why solid ice floats on liquid water.
And the implications of that one structural detail are they're monumental. If ice were denser than water, lakes and oceans would freeze from the bottom up.
Life as we know it would be impossible. Aquatic ecosystems would be crushed every winter, and the oceans might never fully thaw.
So the nature of life on this planet is dictated by the open lattice created by hydrogen bonds. That's incredible.
We can describe it very precisely, of course. It belongs to the space group P63 But conceptually, just visualizing those linked tetrahedra is what really matters.
And it has a cousin, a metastable form called diamond cubic ice, or ice, IC.
That's right. If you look at the diagram for that one in figure 25.1b, the arrangement of the oxygen atoms is a perfect mirror of the diamond structure.
But instead of carbon atoms at the lattice points, you have whole H2O molecules.
Exactly. The unit cell side length, A, is about 0.635 nanometers.
And beyond these perfect crystals, you can also get amorphous or non-crystalline forms of ice.
You can.
Yeah.
We can create low-density amorphous ice, LDM, and high-density amorphous ice, HDM. And the difference in density is striking.
What are we talking about?
LDM is about 0.94 grams per cubic centimeter at atmospheric pressure.
Yeah.
But if you compress normal hexagonal ice at a very low temperature, around 77 Kelvin, you can achieve HDM with a density of 1.31.
Wow, that's a huge difference. You're getting structurally distinct versions of the same molecule just by playing with pressure and temperature.
You are. And the source also mentions this amorphous 2 transition. If you take that low-density amorphous ice and just gently heat it to 17 Kelvin,
Just 17 Kelvin.
at 0 pressure, it transforms into a whole new amorphous phase. This isn't just a lab curiosity. This is hugely relevant to planetary science.
Because you've got vast quantities of ice on moons or distant planets that are being subjected to these wild pressure variations.
Exactly. Understanding these amorphous transitions helps us model the geology of these icy worlds.
Now, before we leave water, there's a technical challenge mentioned in the text. It's hard to find the hydrogen atoms in the crystal structure because they're so light, they barely scatter X-rays. How do crystallographers get around that?
They use a very clever trick involving isotopic effects. Instead of using regular hydrogen H, they substitute its isotope, deuterium D.
So heavy water.
Heavy water, right. Deuterium has a much, much larger cross-section for neutron scattering than hydrogen does. So when you use neutrons instead of X-rays, that chemical substitution makes the deuterium atoms light up. It allows for a much more precise structural determination.
That's a great trick. Okay, let's shift gears from the complex structure of water to the rigid linear molecule of solid CO2 or dry ice.
Right. Carbon dioxide is a simple linear molecule. You have one carbon atom in the center between 2 oxygen atoms. The whole thing is about 0.24 nanometers long.
And a linear molecule like CO2 has no net dipole moment. The charge is all symmetric, but the bonding is still really important for the crystal structure.
It is. The carbon is double bonded to both oxygens,
Mhm.
and you have these remaining lone pair electrons on the oxygens that create a specific non-uniform distribution of charge.
So even though it's not polarized end-to-end like water, it has what's called a molecular quadrupole moment.
Correct. Conceptually, it means you have these attractive regions extending out from the ends of the molecule and also from the middle. And that quadrupole moment is what guides how the molecules pack together in the solid state.
And how do they pack?
Solid CO2 forms a primitive cubic crystal structure IO4. If you look at the diagram, figure 25.2b, you'll see the linear CO2 molecules are oriented diagonally within that cubic cell.
So they're all tilted.
They're all tilted in specific directions to maximize that quadrupole interaction energy.
And that geometry changes under extreme pressure,
It
right?
does. At about 11.8 gigapascals, there's a transition to an orthorhombic phase. And the key structural shift is that the molecules tilt even more. They lie in the YZ plane, inclined at about 52 degrees with respect to the C-axis.
Which is what you'd have to do to pack them in more tightly, I suppose.
It's the only way to achieve the higher packing density that's demanded by that kind of extreme pressure. It's a great example of how molecular solids have to shift their orientation, not just compress, to use space efficiently.
Okay, next up in the text, hydrocarbon crystals. And the focus here is on benzene, C6H6.
Right. So now we're dealing with carbon compounds in chains, or in this case, rings. And the carbon bond length itself is a really good indicator of the bonding strength. It can range from 0.154 nanometers for a single bond down to about 0.12 for a triple bond.
And benzene is the quintessential planar aromatic hydrocarbon. Its famous hexagonal ring structure, which you can see in figure 25.3a, shows that all the carbon bonds are the exact same length.
They are, about 1.397 angstroms. And that length is intermediate between what you'd expect for a single bond and a double bond.
And that uniformity is because of electron delocalization, right?
Yeah.
The extra electron on each of the 6 carbon atoms doesn't belong to any one bond.
It doesn't. It resides in these delocalized pi bonds that basically orbit the entire ring as a whole.
And that's what gives benzene its incredible stability.
Its stability and also its response to magnetic fields. When you put it in a magnetic field, those electrons circulate and induce what's called a diamagnetic ring current. It's a phenomenon explained by Lenz's law.
So in solid form, benzene has a few different allotropes.
At least 3. The lowest pressure one is orthorhombic, with the space group PBA. And describing the crystal packing, which you can see a representation of in figure 25.3c, it really requires you to visualize these flat hexagonal rings fitting together like intricate puzzle pieces.
And they're stabilized by weak hydrogen bonds between the hydrogens on adjacent molecules.
Correct. It's a very efficient packing arrangement.
Okay, let's move on to one of the most structurally fascinating forms of self-assembly, clathrates.
The word itself, clathrate, is generic. It just means caged. It describes any compound where one component forms a cage-like structure that surrounds and traps some other guest molecules.
And we often encounter these as ice clathrates or gas hydrates.
That's right, where a network of tetrahedrally bonded H2O molecules creates these large cavities that can hold gas atoms or small molecules like CO2 or, very commonly, methane.
And there are 2 main types of these ice clathrates mentioned. Type I sounds incredibly complex.
It is. It's a cubic structure with a lattice parameter A of about 1.2 nanometers, and it contains 46 water molecules. But the amazing part is the cavities it forms.
Okay, help me visualize this geometry.
Imagine building a structure out of polyhedra. 20 of the cages are pentagonal dodecahedra, so 12-sided figures with pentagonal faces.
Okay, like a soccer ball, almost.
And then 6 of the other cavities are truncated octahedra, which are 14-sided figures. It's this vast open framework built purely to encapsulate something else.
And type 2 is even bigger and more complex.
It is. It's also cubic. A is about 1.7 nanometers, and it has 136 water molecules. It uses 16 of those pentagonal dodecahedral cages and 8 even bigger hexadecahedral cages.
And this structural ingenuity is not just a curiosity, it has major technological relevance.
Huge. These clathrates are being heavily studied for their thermoelectric properties. When you put alkali metals into silicon or germanium hosts, they form these same type I and type 2 structures.
So the trapped guest atoms can scatter heat-carrying phonons very effectively, while the framework itself remains conductive to electrons.
Which is the perfect recipe for a high-efficiency thermoelectric material, a material that can convert heat directly into electricity.
That's a fantastic transition into the next topic, amphiphiles and micelles, which really continues this theme of self-assembly in water. We need to be precise with the terminology here.
Absolutely. So hydrophobic means water-hating. These are molecules that want to separate from water.
Like oil.
Exactly. And hydrophilic means water-loving, molecules that are attracted to water. An amphiphile, or surfactant, is a molecule that has both parts, a hydrophilic head and a long hydrophobic tail.
And when you put these molecules into water, they have to arrange themselves to minimize the total energy. The hydrophobic tails hate the water, so they try to reduce their contact area.
While the hydrophilic heads love the water and want to be in contact with it, the result is spontaneous self-assembly.
And the main driving force is actually entropic, isn't it? It's about maximizing the disorder of the water by limiting how much of it has to form an ordered layer around those hated hydrophobic
That's a
tails.
huge part of it. And this microphase separation results in these ordered aggregates called micelles. You can see the main types in figure 25.5.
Right, so you have A, spherical micelles, where all the hydrophobic tails cluster on the inside, completely shielded from the water.
Then you can have B, cylindrical micelles, which are just elongated versions of the same idea.
And finally, you can get C bilayers, which are these two layers of molecules arranged tail to tail. And these can form huge sheets, which are basically the foundation of all cell membranes.
Absolutely. And the optimal number of molecules in a given micelle, the aggregation number, is determined precisely by this energetic and entropic balance.
Okay, that wraps up our look at these simple molecular structures and brings us to section 2, polymers. This is arguably the most industrially relevant class of molecular solids we'll talk about.
Without a doubt. So polymers are these massive molecules, macromolecules built from small, repeated chemical units called mers or monomers.
A classic example is polyethylene, just a long, long chain of carbon atoms, each with two hydrogens. And these chains can be thousands, even tens of thousands of atoms long.
Right. When the chains are shorter, say less than about 50 monomers, we usually call them oligomers instead.
Now, because the polymerization reactions that make them are statistical, you don't get chains of perfectly uniform length, so we have to use averages to characterize the material.
We do.
Hmm.
And there are two critical averages to understand. The first is the number average molecular weight, m-bar.
This is just the simple arithmetic average, right? You sum up the weights of all the chains and divide by the total number of chains.
Exactly. It's calculated based on the number fraction of chains of a certain weight, but then there's the weight average molecular weight, m-bar w.
And this one gives more statistical weight to the heavier, longer chains.
It does. It's calculated by summing the number of chains times their molecular weight squared, divided by the sum of the number of chains times their molecular weight.
So why do we need both? What does the difference tell us?
It matters hugely for mechanical properties. Things like melt viscosity or tensile strength are often dominated by the longest chains in the sample. So the ratio of the two, the polydispersity index, tells you how broad the distribution of chain lengths is.
A high ratio means a very wide spread, which can really affect how you process the material and what its final properties are.
Precisely. Now, moving to classification, we can first classify them by their morphology or the degree of branching. You can see this in figure 25.7.
Right, so you have linear polymers like high-density polyethylene, HDPE. It's just a single backbone, so these chains compact together very tightly, and they tend to be more crystalline.
Then you have branched polymers like low-density polyethylene, LDPE. Here you have secondary chains that sprout off the primary backbone.
And all that branching prevents them from packing efficiently.
Right, which is why LDPE is less crystalline, it's softer, and much more flexible than HDPE.
And finally, you have network or cross-linked polymers. This is where you have strong primary chemical bonds that actually connect adjacent chains together.
It locks the whole structure rigidly in space. These are often your thermosetting polymers, or the fixed structures you find in vulcanized rubber.
We also classify them by their thermal behavior.
We do. Thermoplastics are those linear or branched polymers held together by weak van der Waals forces. They soften when you heat them, and you can remelt and reshape them over and over. Think of a plastic bottle.
Then you have thermosetting polymers, or thermosets. These are irreversible.
They're cross-linked by strong chemical bonds. Once they are cured or set, that's it. You can't remelt them without completely degrading the material. They're typically much stronger and more brittle.
And elastomers, like rubber, are a special class of weakly cross-linked thermosets. The crosslinks are sparse enough that the chains can stretch dramatically.
And then snap right back to their original configuration, which gives them that huge elastic elongation.
Okay, let's talk about how these things are actually made. The polymerization reactions.
There are two major types. The first is chain reaction, or addition, polymerization. This is a very fast process that happens in three distinct stages: initiation, propagation, and termination.
So initiation. This is where a free radical, something with an unpaired electron, attacks a monomer's double bond.
It breaks it open and transfers that free radical to the end of the monomer, which is now the start of our growing chain.
Then comes propagation. This is the repetitive growth phase.
Right. The radical on the end of the growing chain just keeps attacking successive monomers, adding them one by one.
Hmm.
The driving force is that you're converting unstable double bonds in the monomers into very stable single bonds in the polymer chain.
And finally, termination, which is when the process ends. This usually happens when two of these growing radical chains find each other and react.
They can either combine, forming one long chain, or one can abstract a hydrogen from the other, a process called disproportionation, which quenches both radicals.
And the second type of polymerization.
That's step reaction or condensation, polymerization. This is kinetically very different. It's a much slower process.
Instead of one chain growing really fast, you have monomers reacting to form dimers, which then react to form trimers, and so on.
Exactly. And the key differentiating factor is that each time a bond is formed, a small molecule byproduct, like water or HCl, is produced or condensed out.
The classic example given is nylon 66.
Right. You have hexamethylene diamine reacting with adipic acid. There are two end groups link up to form an amide bond, and a molecule of water is kicked out. And the polymer just grows slowly as these end groups continue to find each other and react.
Now, beyond just the chemical bonds, the actual physical arrangement of the polymer chain in space has a huge impact on the final material's properties. Let's talk about spatial configurations or stereochemistry.
This is really important. For polymers made from monomers, where one hydrogen is replaced by some other side group, which we'll call R1, the way those R1 groups are arranged relative to the carbon backbone is critical.
It determines whether the polymer can crystallize or not.
It does. If all the R1 side groups lie on the exact same side of the main carbon chain, which is often drawn in a zigzag fashion, we call that polymer isotactic. You can see this in figure 25.9.
Okay, all on one side.
Then, if the side groups alternate regularly from one side to the other like a perfect zipper, it's called syndiotactic.
And both of those are highly regular arrangements, so they can pack efficiently and form crystals.
That's right. But if those R1 groups are just arranged randomly, pointing out in every which way, the polymer is acanotactic.
And that random arrangement makes it impossible for the chains to align, so they almost always remain amorphous.
Exactly. And the difference between an isotactic polymer, which might be a rigid engineering plastic, and its atactic cousin, which could be a useless flexible goo, is immense.
This inherent flexibility of the chain leads us to one of the most important conceptual models in all of polymer science, the random walk model.
It's vital, because we can't determine the precise location of every single atom in an amorphous polymer chain. The chain itself isn't a rigid rod. It's constantly wiggling and coiling.
So we have to use statistical mechanics to describe its average structure.
We do. We model a polymer strand of N monomers, each of length L, as a series of steps where the direction of each step is completely independent of the last one. It's the classic analogy of a drunkard's walk.
Okay, so let's try to ground this for the listener. Imagine you have a very long piece of yarn, and you just drop it in a box. It's all tangled and coiled. The distance between the two ends is definitely not the total length of the yarn.
Exactly. And the key result from the statistical mechanics, which is in box 25.4, is the root mean square end-to-end distance. If the chain were a rigid rod, this distance would grow linearly with the number of monomers, N.
But it doesn't.
It doesn't. Because of the random walk nature, the average end-to-end distance of the tangled strand grows as the square root of N times L.
That square root of independence is the crucial takeaway. It's not linear, it's statistical.
And that result is absolutely critical for understanding everything from why polymers are elastic, they can stretch and recoil, to why even a small amount of a long-chain polymer can make a liquid incredibly viscous.
Okay, next up, copolymers and self-assembly.
Right, so a homopolymer is made from just one single repeating monomer unit. A copolymer is produced from two or more distinct monomers, which we can call A and B.
And you can arrange them in several ways. You can have a random copolymer where A and B are just mixed in randomly.
You can have a periodic one where they repeat in a strict sequence like AB, AB, AB.
And then you have block copolymers where you have long segments or blocks of just A monomers connected to long blocks of just B monomers.
And these block copolymers, especially the linear diblock ones, are where self-assembly gets really sophisticated and interesting.
Because the two blocks, say polystyrene and polyethylene oxide, are chemically distinct, they're incompatible, they're like oil and water.
But, and this is the critical part, they are still covalently bonded together in the same chain, so they can't just separate into two big layers.
They can't macrophase separate, so instead they undergo microphase separation.
Exactly. They separate locally on the nanoscale
Yeah.
into these highly ordered, beautiful microstructures.
And this allows us to tailor structures at the nanoscale. Depending on the relative lengths of the A and B blocks and the concentration, the material will spontaneously form specific morphologies.
Spheres, cylinders, interconnected gyroids, or lamellar sheets. It's incredible.
This ordering is shown really well in the conceptual phase diagram in Figure 25.0 for an amphiphilic block copolymer in water.
It is. You plot temperature against the copolymer concentration. At very low concentration, you just have a disordered solution of micelles.
But as you increase the concentration, the order increases dramatically. You pass through a phase of highly ordered body-centered cubic spheres.
Then you transition to a hexagonal phase of cylinders, and finally, at very high concentration, you get a lamellar or layered phase.
And the technological application of these lamellar structures, for instance, is huge for making nanocomposites.
Yes, as discussed in box 25.5, the layered polymer can act as a host to sequester or organize nanoscale inclusions like gold nanoparticles or silica particles.
So you create this composite material where you can precisely position the nanoparticles to take advantage of their unique magnetic or optical properties while still relying on the bulk strength and flexibility of the polymer host.
It's true structural engineering at the atomic scale.
Now for something you might not expect. Conducting and superconducting polymers. We just established that most polymers are fantastic electrical insulators because their electrons are all locked up in localized bonds.
Right, so to get conductivity, you have to find a way to delocalize those electrons, to let them move freely along the polymer chain.
And this is usually achieved by creating a chain with alternating single and double bonds, known as pi bonds. This creates a sort of one-dimensional electron highway.
The primary example is polyacetylene. It's formed by polymerizing acetylene gas, and it exists in two forms, or polymorphs, cis and trans, which you can see in figure 25.11.
The trans form looks more stable. It has this clean sawtooth arrangement of carbon atoms. The cis form looks a bit more crumpled.
It is. And while polyacetylene is intrinsically a semiconductor, you can boost its conductivity enormously through doping.
Which is adding either electron donors or electron acceptors.
Exactly. This process creates mobile holes or electrons that can act as charge carriers, and the conductivity can increase at many orders of magnitude.
Going a step further, this search for conductivity led to the discovery of the very first organic superconductor back in 1973, a material called TTT-TCNQ.
Yeah, tetrathiafulvalene tetracyanoquinonetaminethane. It's a mouthful.
It is.
And it's not a polymer in the traditional sense. It's a charge transfer salt that forms a one-dimensional crystal. You have these alternating cyclic molecules of TTF and TCNQ that stack up in parallel, creating these linear chains that run along the C-axis of the crystal.
And in its solid form, with these chains all aligned, it actually exhibits metallic conductivity along that C-axis direction at room temperature.
It does. Electrons are transferred between the TTF and TCNQ stacks. And while its superconducting transition temperature, its TC is very low, below 5 Kelvin C, its discovery was revolutionary.
It proved that organic materials could even be superconductors, which spurred a whole new field of research.
It did, and it led directly to materials like the fullerides, which we'll get to in a moment.
And finally, in this section, we have polymeric derivatives of fullerenes. So here we're trying to integrate the C60 buckyball molecule directly into polymer architectures.
Right, to take advantage of its unique properties. Researchers have come up with several architectures, which you can see in figure 25.32. You can have a simple linear chain with C60 molecules right in the backbone.
Or you can have a fullerene-grafted polymer, where the buckyballs are attached as side chains.
Or even complex fullerene-containing network structures. These are highly controlled, often dendritic or starburst polymers, all designed to impart some new electronic or mechanical function to the bulk material.
That kind of structural complexity is a perfect bridge into Section 3, biological macromolecules. Nature's own polymers, starting with the foundation of all life, DNA and RNA.
DNA, deoxyribonucleic acid, and RNA, ribonucleic acid R, along with proteins, the essential machinery of life. And arguably the greatest structural achievement of the 20th century was solving the double helix structure of DNA in 1953.
A feat by Watson and Crick that was only made possible by the absolutely critical X-ray diffraction data generated by Rosalind Franklin.
Absolutely. Structurally, DNA is a polymer, and its monomers are called nucleotides. A single nucleotide has three parts: a phosphate group, a 5-carbon sugar called deoxyribose, and a nitrogen-containing base.
And there are 4 of these nitrogen bases in DNA, as you see in figure 25.14. Adenine A and guanine G are the larger 2-ring structures called purines.
And cytosine C and thymine T are the smaller single-ring pyrimidines.
The backbone of the DNA molecule is formed by linking these nucleotides together with incredibly strong phosphodiester bonds. This creates a very stable chain of alternating sugar and phosphate groups.
That forms a single helix, but the biological magic comes from the pairing, the double helix. And what defines the entire structure is the rule of complementary base pairing, shown in figure 25.1c.
Adenine always pairs with thymine, and guanine always pairs with cytosine, A with T, G with C.
Always. And that pairing mechanism is stabilized by hydrogen bonds. The AT pair forms 2 hydrogen bonds, and the slightly stronger GC pair forms 3.
So if you visualize the final structure from figure 25.17, it's this iconic spiral staircase. The sugar phosphate backbones are the winding handrails on the outside.
And the paired bases form the rungs, positioned flat, perpendicular to the axis. These rungs are separated by 0.34 nanometers, and the entire structure makes a full twist every 3.4 nanometers.
And the profound biological relevance of this precise crystallographic structure is that it immediately explains replication. Because A always pairs with T and G always pairs with C, the 2 strands are perfect complements of each other.
So when the strands separate, each one can act as a template to dictate the structure of a new complementary strand. It's the structural mechanism for genetic inheritance.
Okay, let's shift to slightly larger biological structures. Viruses.
Right, a virus is a parasitic entity. It's made of nucleic acid, either DNA or RNA, which is protected by a protein shell called the capsid. The complete infectious particle is called a virion.
And based on how protein subunits assemble, viruses are classified into 3 major symmetry classes.
You have icosahedral viruses like herpes, helical viruses, which are rod-shaped like influenza, and complex viruses, which have lower, less geometric symmetries.
Let's focus on the icosahedral ones. An icosahedron is a shape with 20 triangular faces and 12 vertices. Now, if every single protein subunit were chemically identical and had an identical bonding environment, you could only fit exactly 60 subunits onto this structure while maintaining perfect symmetry.
But many large viruses have hundreds of protein subunits, and they have very limited genetic material to work with. This is where the brilliant theory of quasi-equivalence, proposed by Casper and Klug in 1963, comes into play.
So they're kind of cheating symmetry.
In a way, yes. Since they can't have strict chemical identity for all the subunits adopt quasi-equivalent bonding environments. They're geometrically close enough to assemble into a visually perfect icosahedron, even though the chemical bonds holding them together aren't all identical.
And the geometry of this is modeled using a honeycomb lattice, a 6-squared lattice.
It is, which you can see in figure 25.18. We label the center of the hexagons with lattice points, HHK. And this leads to the classification system, the triangulation number, or T number.
So T is the number of lattice ports contained within one of those equilateral triangles that forms a face of the icosahedron.
Correct. And it's calculated by the formula T equals H squared plus HK plus K squared. This number is like a blueprint. It tells you exactly how many subunits are required and how they have to be arranged to build a stable capsid. T1 is 60 subunits. T3, which you get of H1 and K1, means you need 180 subunits.
It's an incredible application of pure structural mathematics to biology. Now, what about the helical viruses? The famous example is the tobacco mosaic virus, TMV.
TMV was one of the very first virus structures ever solved. And it's elegant in its simplicity. It's just a single type of protein molecule that self-assembles around a single helical strand of RNA.
The virion itself is rod-shaped, with a 4-nanometer cylindrical hole running right down the center.
And the key structural detail is that the protein subunits, about 16 1/3 of them per helical turn, just self-assemble around that RNA backbone. The schematic in figure 25.20 shows this perfect repeating arrangement. It's a beautiful example of molecular self-assembly.
That complexity of carbon structures leads us right into our next section, section 4, fullerene-based molecular solids. We'll start with C60 and C70.
Right. So fullerenes are synthesized by techniques like vaporizing graphite. The C60 molecule, the buckyball, is this perfect molecular unit. And in solid form, these discrete spheres are held together just by van der Waals forces.
And at room temperature, these pristine C60 molecules form a face-centered cubic, or FCC, lattice. The solid is called fullerite.
And the reason it can maintain that high FCC symmetry at room temperature is crucial. The C60 molecules are spinning. They're rotating incredibly rapidly.
So we can treat them as perfect pseudospheres, which naturally want to pack in an FCC arrangement to maximize density.
Exactly. But that rotation stops at lower temperatures. Below 249 Kelvin, the spinning ceases and the molecules lock into a specific orientation, and the structure transforms to a less symmetric, primitive cubic structure. It's a classic order-disorder phase transition.
And C70, which is slightly elongated like a rugby ball instead of a perfect sphere, crystallizes differently.
It does. At room temperature, it forms a hexagonal close-packed, or HCP structure. It's a great example of how a tiny change in the molecular geometry dictates the entire bulk crystal arrangement.
Now let's talk about fullerides. These are compounds you get when you dope C60 solids with alkali metals. And
Yeah.
payoff here is huge, high-temperature superconductivity.
It is. The alkali metal atoms, potassium, rubidium, cesium, don't replace the C60. They intercalate. They wedge themselves into the empty spaces, the interstitial voids within the SCC lattice.
Specifically, the octahedral and tetrahedral sites.
Right, and the key composition to remember is M3C60, 3 metal atoms per buckyball. At this composition, they fill all the available interstitial sites. The structure remains FCC, but its electronic properties are completely transformed.
And that transformation results in superconductivity at what were, at the time, remarkably high temperatures.
They were. K3C60 has a transition temperature TC of 18 Kelvin. RB3C60 goes up to 28 Kelvin, and CS3C60 reaches 30 Kelvin. These are the highest TCs ever seen in an organic-based conductor.
And the binary phase diagram in figure 25.24 shows just how sensitive this all is to the exact composition.
It does. It details all these different phases, alpha, beta, delta, but the most important insight is that the superconducting FCC phase only exists within a very narrow composition window, roughly between F3 and F4.
If you stray from that very precise recipe, you lose the superconductivity.
You do. It's a delicate link between the molecular structure, the level of doping, and the resulting quantum properties.
Okay, our final structural subject, and it's a big one, carbon nanotubes, or CNTs, discovered in 1991.
These are truly revolutionary materials. They're essentially carbon fibers made of graphitic sheets that have been rolled up into perfect cylinders.
And their properties are just phenomenal. A Young's modulus of over 1 terapascal, a tensile strength of over 200 gigapascals. They are one of the strongest materials ever discovered.
To understand their structure, you have to start with a single 2D sheet of graphene, which is just a hexagonal net of carbon atoms. This sheet is defined by 2 basis vectors, A1 and A2.
A CNT is then conceptually constructed by taking this sheet and rolling it up.
And its structure is classified mathematically. You can. The formula is given right in the text. But this is perhaps the most incredible lesson in the entire chapter.
What's that?
That simple geometric formula, based on 2 integers, n and m, determines everything. It determines whether the nanotube will be a metal with incredibly high electrical conductivity, or if it will be a semiconductor. The crystallographic symmetry is the electronic property.
It's astounding. We've covered so much ground, but none of this knowledge would exist without the pioneers who mapped these molecules. Let's take a moment for Section 5, the historical notes.
We have to start with Francis Harry Compton Crick, a British physicist and biologist who was instrumental in applying X-ray diffraction to biological molecules, and of course, famously collaborated with Watson to solve the DNA structure in 1953.
And we simply cannot talk about DNA without honoring Rosalind Franklin. She was a British physical chemist who generated the X-ray diffraction data, especially the famous Photo 51, that was absolutely essential for determining the double helix.
Her contribution was fundamental. She also did significant work on the crystallography of viruses and carbon. And while she passed away tragically young, before the Nobel Prize was awarded, her meticulous structural work really laid the foundation for all of modern molecular biology.
And finally, Dorothy Crowfoot Hodgkin, another brilliant British chemist and a true pioneer of protein crystallography. She solved the structures of incredibly complex molecules like cholesterol, penicillin, vitamin B12, and her crowning achievement, the structure of insulin.
She received the Nobel Prize in Chemistry in 1964. Her work showed that even the most complex biological macromolecules could be solved with X-ray crystallography, which really paved the way for the entire field of structural genomics.
That was an absolutely comprehensive deep dive across the entire spectrum of molecular solids. Let's try to quickly review the major themes we've established.
I think our journey started with the defining characteristic, the weak link. You have strong internal covalent bonds, but the solid is held together by these weak external forces, van der Waals and hydrogen bonds.
And that determines everything, from the low melting points to the softness of these materials. We saw how that weak linkage creates the beautiful but anomalous low-density structure of hexagonal ice.
And the tightly packed, diagonally oriented structure of dry ice, where the quadrupole moment is guiding the arrangement.
The theme of self-assembly was huge, linking the cage structures of clathrates to the microphase separation we see in micelles and block copolymers, all driven by this need to minimize surface energy and maximize entropy.
We covered the vast landscape of synthetic polymers, defining their chain configurations, isotactic, syndiotactic, atactic, and contrasting the different polymerization methods.
And crucially, we came to understand the statistical nature of these materials through the random walk model, where the chain's end-to-end distance scales not linearly, but as the square root of n.
And then we saw the pinnacle of precision in biological structures, the absolute necessity of complementary hydrogen bonding, AT and GC, to define the exact geometry of the DNA double helix.
And the elegant mathematics of quasi-equivalence and the triangulation number, T, that are used to classify the structure of viral capsids.
Finally, we covered the marvels of carbon allotropes, the rotational freedom in C60 fullerite, the incredible achievement of high-temperature superconductivity in doped fullerides like K3C60.
And the unbelievable mechanical and electronic properties of carbon nanotubes.
So, at the end of the day, what is the fundamental takeaway for you, the learner? I think it has to be the extraordinary and delicate control of function that is achieved through nothing more than molecular geometry.
Think back to the carbon nanotube. Its chemical composition is as simple as it gets. It's pure carbon. But the way that two-dimensional sheet of graphene is rolled into a cylinder dictates whether that material is a metal or a semiconductor.
That small difference in crystal symmetry, defined by two integers, n and m, and translated into a chiral angle, that is the difference between a highly conductive wire and a field effect transistor.
And that's our final provocative thought for you to take away. How does such a minute structural difference, a variation of just a few degrees in the twist of a sheet of carbon, profoundly determine the electronic destiny of a quantum material? It's the most striking example of crystal symmetry acting as fate at the nanoscale.
Thank you so much for joining us for this extensive deep dive into the architecture and function of molecular solids. We hope you now see the weak forces all around you in a whole new light.
Until next time.